All right, good morning. Let's go ahead and dive into our physics text here. Uh, Unit 1, Chapter 1, Understanding and Describing Motion. This is all part of the unit titled Forces and Motion. Okay, and if we take a really quick look through here, 1.2 is going to discuss Newton's laws. We'll talk about vectors and scalars as ways to describe motion in 1.3. We'll look at solving motion problems 1.4, and we'll talk a little bit about the conservation of momentum in 1.5. Okay, so that's a bird's eye view. And let's jump right into Explore number 1. Okay, looks like we have 2 Explore pages. So let's draw out our lines. And go ahead and put down the date. All right. Today's date for this recording is 11/14/2023. I'll let you write down the date that you're actually writing this down and listening to it, okay? The essential question: what are frames of reference and how do they relate to motion? Question mark, okay. Let's go ahead and have you right now talk about what you know. Okay, so go ahead and pause the video and write down what you know. Okay. All right, hopefully you've paused the video and you have a little bit of information that you have written down there. Let's go ahead and jump into the notes, okay? And hopefully we'll add to your knowledge there. Okay. Okay, when we're talking about frames of reference, oftentimes we're going to speak about coordinate systems. You've heard this term before, perhaps in a math class. Your x and y axis is a familiar coordinate system. Okay, physicists describe the position of objects with respect to frames of reference. Okay, describe positions of objects relative to respects to frames of reference. A frame of reference provides a system. Okay. For identifying an object's location. Okay. So that's really what they do. They provide a system of coordinates for identifying an object's location. Okay. So you may remember here, if I were to draw a coordinate system, you could have a y-axis, right? Oftentimes we call this your y-axis. You can have an x-axis, and you can have even a three-dimensionality aspect to it, what we would call a z-axis, a z-axis. And things can move along any of these axes points, and we can describe three-dimensional movement this way. Okay, so in this case, we might describe an object's location, movement in all three terms. It doesn't have to be this way. We could have just purely a two-dimensional axis. Okay. Note, sometimes we only describe using one or two axes, right? In your textbook, they talk about somebody who is bungee jumping, right? Somebody who is, i.e., for example, you could have a stand, and you could have a person at the top, and they're going to bungee jump. And what happens is when they jump, they're going to go down, and the bungee is going to then pull them back up. Maybe not as high, and each time it's a smaller movement, but it's just movement along the y-axis. This is basically just the y-axis, right? Sometimes we may describe something like somebody shooting an arrow. You have somebody, and they have a bow and arrow, and they're going to shoot the arrow, right? And we describe the motion as the arrow goes something like this. And we would say that there was a y component, and we could also say that there was an x component. And this would be like a two-dimensionality kind of aspect. All right. Okay, so the next thing we need to talk about here then is, let's talk about, oops, clear the screen there. Let's talk about this whole idea of inertial and non-inertial frames of reference. Okay, so we talked about using X, Y, and Z. Got some videos. Here, this is the last part of our lecture today, okay? So let's do this here. Let's draw our line down here. Oops. Okay, I'm just going to take that down. And we're going to say Roman numeral 2. This will be inertial versus non-inertial frames of reference. Okay. So as we can see here in the text, physicists distinguish between two types of frames of reference. The first type is your inertial, and the second type is your non-inertial. The difference has to do with the first of Newton's laws of motions. Okay, And if you are curious about that, you can always click on the vocabulary word there. I think because I'm in tablet mode, it doesn't let me click on these things there. But you can take a look at Newton's laws. All right. The first law, an object in motion stays in motion unless acted on by a force. An object at rest stays at rest unless acted on a force. Okay. Okay, so what does our text say there? Let's go back. Two types of frames of reference, right? The difference has to do with the first of Newton's laws of motion, which are discussed. The first law applies in the case that there are no unbalanced forces acting on an object. It says that objects remain motionless if they're at rest. Okay, so um, that has to do with this one called the inertial frame of reference here. Okay, is one that acts in accordance with the first law. Okay, so we're going to say capital A, and we'll talk about inertial first, the inertial frame of reference. Okay, and we want to say this one acts in accordance with Newton's first law. Okay, and again, objects in motion tend to stay in motion. Objects at rest tend to stay at rest unless a force acts on it. Okay, unless a force acts on it. So in this frame of reference, there is a constant velocity, which would have zero magnitude. That means there's no change in the speed. There's no change in the direction. Okay, so what do we want to say here? Velocity is constant. No. Okay, with a zero magnitude. Therefore, magnitude. Okay, which is AKA direction change. Okay, its velocity does not change in magnitude or in direction. Okay. Objects moving within the inertial reference frame may accelerate, but the frame itself does not. Okay, so that's probably an important aspect there. Okay. Okay, so two, let's just write this down here. Objects within a frame of reference objects within a frame of reference may accelerate, but the frame itself does not. This is a big but. But the frame itself does not. Think about being in an elevator, perhaps, and the elevator is moving at a constant speed. You can walk around in the elevator, and for the most part, you are unaware that something is happening unless the elevator stops or suddenly falls. Maybe it's the same thing as being on an airplane or on a train or even in a car. These vehicles, if they're moving in one direction, they're moving at a constant speed, you would be unaware that there is anything going on with regard to the frame, the bigger frame, even though you as an object could still do things within that frame of reference. Okay, so that's, we'll just say examples. Being in a vehicle moving at constant speed and direction, that is the frame. You, as an object, are not aware of what's happening on the outside. On the outside. Okay. This is juxtaposed or in contrast to the inertial frame of reference. And let's see here. Well, here we go. However, if the speed or direction of the train did change, then the frame of reference would become non-inertial. Okay. As soon as the speed or direction of the vehicle changes, then the frame of reference, changes. And what does it change to? It changes to a non-inertial, changes to a non-inertial frame of reference. Sorry, my writing's a little sloppy there, okay? But that's an important point there, okay? This is important, okay? So we've gone from being inertial to becoming non-inertial, okay? Non-inertial. All right, hopefully that helps. And what I'd like you to do right now is write a summary sentence, okay? So, gosh, let me just do that. And let's go ahead. Can I move this here? I can. Draw that line down there. And here we go. A summary paragraph, okay? Actually, let's do that. A summary paragraph. Alrighty, we'll talk to you soon. Bye-bye.